Hello, everyone. This is Mr. Tam back with another episode. We have discussed last time how to analyze certain parts of enthalpy, the factors that actually influence it, and I was introducing you a little bit to the enthalpy graphs. Today, I'm actually going to go through an example so that you guys can actually apply what we learned last time to a specific reaction. So I'm going to do one that you guys may be familiar with. We're going to take just hydrogen in gas form, and we're going to react it with chlorine, one of our favorites because it's just so dangerous. And after we react these two reactants together, we end up with a product known as hydrochloric acid, but we're going to end up with two of them. And this one will be, let's say this one is in gas form as well, just to make our lives a little easier. So as we discussed last time, there's certain parts of this particular graph that we have to understand. This right here is known as the potential energy of the reactants. In this case, we don't really want to assign a number to it because it doesn't really influence the final answer a whole lot. I just wanted to label it so that you guys have an idea of what I'm talking about. This one right here is the end result, or the potential energy of the products. This is just a label qualitatively so that you guys know which parts of the graph I'm referring to. And of course, last time we also discussed the activated complex, which in this case is actually very important. So when these two molecules collide together, they actually end up forming, for a very brief second, this kind of unstable state, where all the atoms are kind of free floating in space, but because they have so much energy, they're so unstable, they're looking to bond right away. For that split second, they are separate. So you'll have, let's say, two H atoms and two chlorine atoms. And this particular state right here is known as the activated complex, which we're going to need to use afterwards. Now, for the sake of argument here, we're going to use some actual numbers. When you actually put some energy in to react these two, it's essentially to give them enough energy to collide and break their bonds. So this part I'm actually going to call bond broken. And essentially I'll put in about 678 kilojoules to break those bonds. This is also known as the activation energy. We're going to label it as E subscript A to make it easier for ourselves. And the bonds formed, when these two atoms come back together, they don't need a whole lot of energy. So there's going to be a lot of excess that's released by the formation of these two atoms into the environment. And in this particular scenario, we're going to have about negative 862 kilojoules of energy released. And that's very important to remember because we're actually going to be comparing the amount that we see here to the amount that is released here. So it's always a comparison of one versus the other. So in step one, I want to break it down into two parts. We know this part as the bonds breaking. So this bond breaking scenario, we have hydrogen plus chlorine gas, and it leads us to the activated complex. Now I'm going to label this activated complex as a C in brackets. Okay, this AC here, let me just write it on the side, refers to the activated complex. And this particular step has a change in H of approximately 678, just like we were labeling earlier. So this is positive. Do you have to put the positive? No. I just like the visual of the positive to help me remember, oh, this part is endothermic. And it's something I'm going to label on the side as well, endo. So the first step, because you end up with higher energy than you started with, it is an endothermic process. It means that the system is absorbing energy. Step 2, on the other hand, is bond forming. And this step starts off with the activated complex being super unstable, leading itself to eventually combine and form the hydrochloric acid we were referring to. And this particular delta H, this step, releases negative 862 kilojoules of energy. And because you are releasing energy from the system, this step right here is considered exothermic. So it is the combination of these two steps that form the overall equation. So what I'm going to do is I'm going to draw a line just to kind of add them up as if they were a math equation. So this actually throws back a little bit to what we call Hess's Law, which we discussed a while ago. So what you end up with is H2 gas combining with chlorine gas, having also the activated complex on the left, which is this one, forming, again, an activated complex, which is found on the right, and my 2 hydrochloric acids, or hydrogen chlorides. Now, if we think back to Hess's Law, we remember that whatever is on the left that's equal to the amount on the right will cancel each other out. They don't really contribute to the reaction and therefore are not necessary. So we can very easily just say, hey, you know what? This activated complex that's on the left goes away, and the activated complex on the right just goes away. So in the end, what are you left with in terms of a reaction? Well, you end up with H2 plus Cl2 gives you 2HCl, which sounds like a very reasonable reaction. Now, what we've done in the past is when we've done Hess's Law, we've added these two energies together, these two right here, and 678 minus 862 essentially give us negative 184 kilojoules. Now, I would like to write this differently for you guys in case some of you prefer to write a thermochemical equation instead. Sometimes we can rewrite this equation as H2 and Cl2. Of course, we don't forget our phases of matter, our gas form. It gives us 2HCl in gas. And of course, because it's exothermic, the energy gets released with the rest of the products. So you have to add in. Sorry about that, guys. I'm just having a little computer difficulty here. You end up with adding 184 kilojoules on the right side. So these two equations are essentially the same thing. Now, what I'd also like to note on the side for you guys here is that if we were to call, if I were to ask you what the activation energy is in this case, that's essentially the amount of energy you need to put into the system to break the bonds. Kind of like if you were behind a hill and you had a soccer ball in front of you, the amount of energy you need to kick that soccer ball for it to go past the hill. So in this case, our activation energy is 678 kilojoules. And if I were to ask you the heat of reaction, I'm going to use RXN for short, the heat of reaction. Well, this is what happens when you add those two energies together, and overall you get a delta H of negative 184 kilojoules. And what that means is essentially your reaction is exothermic overall, because you're always comparing the endo to the exo side and then seeing which one of them ends up giving you a bigger number. Either it's going to be overall positive or overall negative. So that being said, I'm going to just briefly describe to you what happens if you were to have a reverse scenario. So what would happen if I were to, I'm just going to erase all of this so that I can talk about it. Oops, sorry about that, guys. I didn't mean to erase the y-axis. What happens if I were to ask you about the reverse reaction? So basically exactly the same thing, but what happens if we're going in the opposite direction, where we don't start off with the hydrogen and the chlorine and end up with the hydrochloric acid, but instead we start with the hydrochloric acid and go backwards. So I'm just going to briefly talk about that, and I think that'll be that for today. So let me just finish off. I'm going to rewrite that, finish off erasing this. So what happens when I'm talking about a reverse reaction? Reaction progress. Well, you realize that the product actually started off lower. So I'm going to draw the potential energy starting off at a similar level compared to what we talked about earlier. And of course, you have your initial reactant starting off at a higher level. Our level of the activated complex doesn't change, but you notice that all we've done is really just switch the places of the products and reactants. So I have two HCl here reacting together, and this of course gives me the hydrogen I was having earlier plus 2, or the chlorine molecule as well. And of course, the activated complexes don't really change. But what does change is the following. Here, we need to put in 862 to break the bonds. And here we need to take away 678 to form the bonds. And what that ends up actually giving me is an overall delta H, if you add those two numbers together, of positive 184 kilojoules, which basically means that the reverse reaction is an endothermic reaction. Oh, what do you know? The opposite of exo is endo. So what's also important to remember is that the activation energy is, instead of being 678, is 862 kilojoules, because it's more difficult to start the reverse reaction than it is to do the initial forward reaction. So this is basically all I wanted to talk to you guys about today. I hope you found this useful. You can now essentially try the rest of chapter 4 without really much of an issue. Please make sure to try them. If you have any questions, of course, always feel free to email me. And I hope you guys are doing well, that your families are safe. And I will see you in the next episode. So, bye for now.